Okay, I realize not everybody's here, but why don't we go ahead and get started. I realize, you know, sometimes like you can't win for losing. So I made a potato clock. Well, yeah, I made this plastic myself. I have a potato clock. It has worked before. It was working last night. It was working this morning. I was carrying it into the building and I dropped it. It's not working right now. So I wanted to show you the potato clock. You can see the potato clock. And I'll say, oh yes, look at the potato clock, it's working, and put my thumb over the thing so you can't see that it's not working. I'll pass it around. If somebody gets it to work, I have a shiny quarter in my pocket, I will give it to you. Maybe even more, I don't know. But anyway, if you've seen one of these before, essentially the potato acts as kind of like a battery, as a source of energy that can be used to generate electricity. I also wanted to talk about, I'm guessing many of you have heard or seen there's an exciting video of me blowing up a Pringles can somewhat differently than expected. So I wanted to talk about that, especially since you guys are high school teachers and you might do this. If you recall, and I think we did the Pringles can and it worked? Yeah. Okay, so this is the problem with doing everything 7 times, you know, it's kind of, So what happens is, ideally you're supposed to fill the can with hydrogen gas. Hydrogen gas by itself isn't going to burn. There's no oxygen there. So you kind of overfill the can, okay? So I don't know if you noticed, but I really gave it a good jolt each time to kind of make sure that the can was very full. And you fill it in such a way, this is sealed, and you fill it from the bottom so that the gas, which is lighter, displaces the air and the air can flow out. And then when you light it, the flame burns at the top, and it's a lovely reaction. Hydrogen plus oxygen, it's a redox reaction, we'll talk about it. And what happens is, as the hydrogen burns and goes out the top, air comes in to take its place, right? And so eventually you get an explosive mixture in here. And the other thing that happens is as the hydrogen burns, the flame gets smaller and smaller, and the flame eventually goes through the top of the can, and it vibrates a little and makes that kind of noise that is sort of your warning, all right? This is, of course, the theoretical ideal, just like the potato clock should work, all right? So it turns out my cylinder of hydrogen was quite low. The gauge, the pressure gauge on the regulator, not very good. So I knew it was low, but you know, I'm like, oh, it'll be fine. So yesterday I filled the can. It was apparently the last gasp of hydrogen. There was very little hydrogen left in the tank. So instead of completely filling it, I just partly filled it. So it already had an explosive mixture in it, right? So I tell the people, oh, you don't have to cover your ears, it'll burn for a minute or two, and you know, so everybody's just sitting there. And I go and light it, and you always light it from the top, and it's open at the bottom, and the flames come out the bottom. So I was still, you know, not super close, but I was a lot closer. Normally I kind of step back, so I'm like 5-6 feet away. As soon as I touched the match to the top of the can, bam, it blew up. And yes, apparently we have it on video. I'm pretty sure I said the word fudge, but another word perhaps was going through my head. So anyway, someone has kindly sent me the video. I only saw it when I got here this morning. I haven't seen it myself yet. So assuming is it on YouTube? Yeah, assuming that it's safe for public consumption, I'll put it on the wiki for you, okay? And does that sound good? Yeah. So, I mean, as teachers, here's our takeaway, let's be serious lesson. This is like, you know, at the end of the show where they get the moral, right? But, you know, the idea is always that you want to be safe because you never know when something's not going to go the way you've got it planned. So when I do this demonstration, I always make sure that the students are not like right up there to see it. Because if something like that happened, that could have been bad if somebody was like right up there to see it. And you know, even though I lit it and I was here, I was still about an arm's length away. I guess what I should have done was, knowing that the tank was low, I should have just sent it off to be refilled. You know, sometimes the desire to sort of eke out the last little bit of hydrogen. You know, I thought, oh, surely this will be fine. I can send it off, and then we'll have a full tank for the coming semester. We'll have a full tank for the coming semester, and I have a good story, okay? So is this good? I've now completely lost the class because you're all just watching the video or trying to earn the quarter for fixing the, has anybody managed to fix the clock? Nah, okay. I'm sorry? Oh. I got a screwdriver. So anyway. Okay, so I wanted to talk about the reaction that's going on. We had this at the end. This is a redox reaction, right? Okay. So if we look at this, we've got our rules up here. Pure elements oxidation states are 0, just to review. If you have a simple ion, so something like sodium plus, the oxidation state is equal to the charge, it's +1. Chloride minus is -1. Copper 2 plus, like I showed you with the silver tree, would be a +2. Hydrogen, typically 1. I'm going to show this slide to the middle and elementary school teachers, so I didn't add that hydrides are -1, but you guys remember that. Oxygen is usually -2. Peroxides, as we know, are -1. The sum of all the oxidation states in a molecule is 0. If you have a complex ion, the sum is equal to the charge. All this is review. I mentioned this at the end, but I didn't put it on the board. But it's kind of a common sense. I'm going to put this on the wiki as well. But you're welcome to film it, and me, and maybe something exciting will happen, and you two will earn YouTube undying fame. And is it on YouTube? Am I going to be like the next internet sensation? Or darn. All right. My children might think, I'm not sure, my children would either be mortally embarrassed and enter the Children Witness Protection Program, or perhaps they would glow in my, reflected light. But anyway, or the light of the exploding Pringles can, something. The last thing, and this is kind of common sense, but we spend a fair amount of time talking about, here's the periodic table. You can look at the periodic table. You can use this idea that things want to be like a noble gas, and so because of that, you can predict simple oxidation states. And so if you've got something and you don't know what it is, and it's on the ends of the periodic table, then it's a pretty good guess that you can probably come up with a oxidation state just looking at what kind of ion might this form, okay? So sodium in the first column, first group, the alkali metals would be +1. Fluoride over in the halogens, group 17, -1. Magnesium in the alkaline earths, +2. Again, I'm guessing this is pretty straightforward. Okay? Does this make sense? Okay. So, I have my crib sheet here, also known as notes. Couple things that we want to look at then. We've already practiced, and we know here the oxidation states for hydrogen and oxygen, because their pure elements are 0. We did water about 57 times, but each hydrogen is +1, and the oxygen is going to be -2, right? Everybody agree with that? Okay. So you can start to look at things like, what is the change? Okay. How many electrons are exchanged here? And remember, we did the exciting demo where I passed out money and then asked for it back. And you guys, I don't think this was the group. One person was like, nobody would raise their hand. And finally somebody said, sure. Finally somebody said, I'll do it for 10. And I was like, I'm still getting it back. And they're like, no, I want a 10. So I happened to have a 10. So we passed a $10 bill back and forth. But how many electrons are being exchanged here? See, everybody's laughing, and all of a sudden, we've got them. Well, so here's the deal. Each hydrogen is going from 0 to +1, right? Everybody agree with that? Okay. And so how many electrons is that? What number electron change is it? Why is it 4? Ah, because I have 2 hydrogens. Yes, okay. You guys are good, so you're skipping ahead. Okay. So that's a 1 electron change. How many hydrogens do I have? I've got 4 hydrogens, so it's going to be overall a 4 electron change. Does this make sense? Everybody got that? Okay. You could do it the other way. You could look at the oxygens, right? Each oxygen is going from 0 to -2. Each oxygen is gaining 2 electrons. There are 2 oxygens, so 2 times 2 gives me 4. Is this good? Okay. I'll give you something that's a little trickier. Can I erase my shame here? All right. Now, this is a balanced equation. And Mn is manganese, for those of you who don't know. Manganese is a transition metal. I probably should have I wanted to have the rules up for you. Do you want a periodic table up? Would that be more helpful? Okay. Rather have the rules? Okay. So manganese is a transition metal. So here's what I would like you to do. First, I want you to figure out oxidation states for all the atoms in the reaction. Okay. Then I would like you to figure out the change in oxidation state for manganese, going from MnO2 to Mn2O3. Okay. And we'll say hydrogen as well, although that's pretty easy. Okay. And then we'll do how many electrons are involved. Okay? Does this make sense? No? No? Okay. So the first one is what you've already been doing, right? Okay. So if you're going to figure out the oxidation state, we could do it for water. We just did it for water. Each hydrogen is what? +1. And the oxygen is -2. Okay? Hydrogen is a pure element. So what's it going to be? Well, pure elements are 0. Remember, when we talk about it's early. Good Lord, it's before 8:30. We don't even have an explosion to wake us up, okay? Although we did have the dropping potato clock. But when we talk about oxidation state, we're comparing the number of electrons to what the atom has in the pure element, okay? So it's kind of what's the change from the pure element. That's a way to think about it. Does that make sense? Pete?
Can we think about it like the oxidation states are different on the product side?
Sure. If it's
and 0 on the product side.
I would agree that they are different on they're going to change. If it's an oxidation reduction reaction, they have to change going from reactants to products.
But like when you did the H2 plus O2,
right?
Then you got water, which is neutral on the other side, right?
Yes, that's true.
It's always going to be neutral on the product side.
It's a good question. The question is it always going to be neutral on the product side? It might be a complex ion, but I would give you a balanced equation, so it would still be a balanced equation. So if you remember like nitrate that we showed, the nitrate was a complex ion. So that wouldn't be neutral if you made nitrate, which you could imagine. Okay? Do you guys want a screwdriver? You have one. All right. Okay. So Does that kind of answer your question?
I think so.
Okay. So if we look at hydrogen, what's the oxidation number for each hydrogen? Well, hydrogen, yeah, I'm hearing plus ones and I'm hearing zeros. It's got to be 0 because it's the element. Does that make sense? If it's pure, if all there is one element, it doesn't matter if it's adamantium, which doesn't exist. Even though adamantium doesn't exist, I can tell you pure adamantium has an oxidation state of 0 because it's the pure element, okay? Does this make sense? And everybody's like, what? Adamantium doesn't exist? All right. Why don't we work out which one do you want to do? MnO2 is probably slightly easier. So MnO2, each oxygen is going to be -2. So the two oxygens together are -4. So the manganese has to be, I'm hearing +2 and +4. It's got to be +4, right? Because the two oxygens are -4. There's 2 of them. Each oxygen is -2. There are 2 of them, so it's -4. To balance it out and get it neutral, the manganese has to be +4. Does that make sense? Oh, thank you. Should we go over that again? Yeah.
I can see why the manganese has to be +4.
Okay.
But can I find that out by looking at the periodic table? Or
No. Remember, we said that things in the middle, the rule didn't really apply to. So it's only things at the end. Manganese, because it's a transition metal, doesn't easily fall into that rule. And even there, I mean, if you're using the periodic table, if you remember in our first lesson, we looked at carbon, and we saw carbon oxidation states from +4 to -4. I think +2, -2, and 0 were in there as well. So, you know, if you look at the periodic table, you could argue for carbon being +4 or -4. But the trick is those are sort of the extremes that you can predict. And oxidation states can sometimes be in between. Nitrogen, for example, has a really wide range, and almost all of them you can find important compounds for. Okay? So the manganese is +4. Does that make sense to everybody? Okay. Are you guys okay to try and figure out what the manganese here is? Everybody see that it's +3? Okay, is there anybody that would like me to go over that it's +3? On the product side. Okay, so again, each oxygen -2, the 3 oxygens together -6, the 2 manganeses +6, half of that is 3. Okay, does that make sense? Okay. So we've now figured out, I would be glad to do it. Let me, sure. So Mn2O3, each oxygen is -2, right? Okay. There are 3 oxygens, so altogether they are -6. Does that make sense? So the 2 manganese together have to be +6 to balance the charge. Okay? And then you say, okay, each manganese is 6/2, which is +3. Does that make sense? Yeah.
I was taught that it just switch crisscross the subscript.
That's certainly, there's lots of ways to figure it out. And so because you know oxygen is -2, so that often works. This also works. So whichever way you like, okay? If you've got a way that works, more power to you, okay? So did everybody see that? You can do the crisscross applesauce, okay? Does this make sense? Okay, so that's another way to do it. All right. Does this make some sense? Okay. Does it make more sense? Okay. So, what's the change in oxidation state for the manganese? We're looking at one manganese atom here. It's going from +4 to +3. So it's a -1 change. Does that make sense? So each manganese gains 1 electron. Does that make sense? It's a -1 change. Thank you, Ben Franklin. The electron is negatively charged. And so each manganese is a -1. We go from +4 to +3. It's a 1 electron change. What do we call gain electron? Reduction. Leo says GER, right? Lose electron oxidized, gain electron reduced. You guys know oil rig? Did I say that one? Oxidation is loss, reduction is gain. I don't know if you like that one better. I kind of like Leo says GER, so I'm a Dumbledore man and a Leo says GER. But anyway, does this make sense? Okay. How about the hydrogen? What's the hydrogen doing? It's gone from 0 to +1. So each hydrogen is losing 1 electron, right? Does that make sense? Poor hydrogen can't lose any more. So gain electron. Does that make sense? Is this good? Okay. Yeah, it becomes more positive, less negative. If it's less negative, it's losing negative things. They're electrons. Okay? I seriously think that life would be easier for electrochemistry and redox if the electron were positive, but it is what it is. Does this make sense? Everybody's fairly clear on this? Okay. What? I'll do another one, yeah. Let's look at the number of electrons. Okay? So, the number of electrons that are being exchanged here, well, each manganese gains 1 electron. How many manganese are there? 2. So it's 2 electrons. Does that make sense? Or each hydrogen loses an electron. There are 2 hydrogens. It's a 2 electron change. Or there are 2 electrons overall, okay? You can't have an oxidation without a reduction. You can't have a reduction without an oxidation. When we passed the money, it wasn't like both people all of a sudden gave up dollar bills and they disappeared. It wasn't like 2 people all of a sudden said, I would like a dollar bill, and it magically appeared, right? One person gave up the dollar, another person got the dollar. One species gives up an electron or electrons. The other species gains the electron or electrons. Does that make sense? Okay? So they always have to be coupled together. If they're not coupled together, you've done something wrong, or you've got a potato clock where they're not actually working. Okay? Does this make sense? It's okay, you don't have to worry too much about it, but thank you for looking at it. Okay? Is this good? Everybody's good? I was like all excited because the wires, it was my kid's potato clock, and the wires, like the ends were all frayed. So I had copper wire along, because who doesn't travel with copper wire, right? Okay, Kevin says of course, right? But so I, go out and get some copper wire and fix it, and it's working, and I'm like all excited. And I couldn't set the time, but that was okay, because I'd move it and it would reset because I'd bump the thing. And so I was like, that's fine, you can just see that it's working. But this is how it goes. All right, how about a practice one with manganese? Is it okay if I erase this? Everybody's good? Okay. How about a practice one with manganese where you have to use rule 6? So this is a so-called half reaction. It is not balanced yet. And frankly, do you want it balanced, or should I just, why don't we're just going to look, this is what's called a skeleton reaction. We're just going to show the thing that's reacting and the thing that's produced, okay? Figure out the oxidation number for the manganese in, this is potassium permanganate, and here, this is manganese metal, okay? And I will give you a hint. Potassium forms a +1 ion. If you have a periodic table, and I saw a few people have a periodic table, it's in group 1, okay? Does that make sense? So, give you guys a minute. This one's easy, okay? Is this good? Questions? No? You're thinking? Thinking is good. Thinking is hard work. All right. Is it still dead?
I can't get it open.
All right. Thank you for trying. Oh, thank you.
Just need a smaller screwdriver.
Okay. Okay. I'm hearing a lot of chatter, which makes me think that you're all very excited that you got the right answer. Should we check? Okay. So, first off, we'll do the confidence building easy one. Pure element manganese, 0. Okay. For the potassium permanganate, each oxygen is -2. 4 oxygens together, -8. The potassium is going to be +1. So the manganese has to be, well, -8 and +1. To balance it out to get to 0, it's got to be +7. Does that make sense? Remember, and we talked about the fact that metals often form cations, or metals like to lose. Okay, so we're going from +7 to 0. How many electrons does the potassium permanganate have to gain to go from +7 to 0? 7. Does this make sense? Okay. Do you want me to balance it the rest? Does anal retentive have a hyphen? There's 8 hydrogens, and you get 4 waters and a potassium out at the end. Okay. Okay. So this is what's called a half reaction, because it's only showing, in this case, is this an oxidation or is this a reduction?
A reduction of.
Yeah, it's a reduction. Manganese is gaining 7 electrons. Does this make sense? Okay. So if you gain electrons, that's a reduction. And that also means that electrons are like a reactant, although you can't really get a bottle of electrons, okay? If you lose electrons, that's an oxidation. And then there, electrons are going to be like a product. Does this make sense? Okay. You guys good? You want to do another one?
Sure.
Another one? Sure. Okay. Everybody okay if I erase? Yes? All right. Again, this is not balanced, right? But we're going to focus on a individual chlorine atom.
I'm going to ask you to go backwards, Charlie, or just give me attention for a second.
Sure. Do you want? You have a question?
Sure, I do.
Okay.
Let's look at the end of that one. If on the product side, this manganese is 0, where'd that plus come from? Because that's
Well,
going to net 0 also.
Sure, but
Was this thing plus to
this
begin with?
no. Here, there's 7 electrons
Right.
and 8 hydrogens, and you get 4 waters. So the 8 hydrogens go to the 4 waters, the 4 oxygens go to the 4 waters, the manganese goes to the manganese. The potassium ion was a positive ion all along because this is really
Okay.
that. So it's just along as a counter ion. Does that help?
All right. Well, if it's a plus all by itself as a single.
It's not changing its oxidation state though. It's a +1 here and it's a +1 here.
Oh. Okay.
The only thing that's changing its oxidation state is the manganese.
Oh, okay.
Does that make sense?
I'm still not clear why. Okay. It doesn't have to equal 0 on the.
It doesn't have to equal. The charge has to be equal. If I add the charges up,
I'm good.
here's -7 and +8. So that's overall +1. Here's 0, 0, and +1. That's overall +1.
Okay.
Okay? You could also write this as 7 electrons plus 8 H pluses plus MnO4 minus gives me Mn plus 4 H2O. This is neutral and that's neutral, if that makes you happier. And then I don't show the potassium because it's a spectator ion. Okay? I was just putting the potassium in to use rule 6. Okay? Okay, you guys good? Can we try chlorine? So, anything here except a pure element? No. So what is it? 0. And I always write each just to make sure that I'm clear that it's, okay, there are 2 of them, but 2 times 0 is still 0. Okay. How about here? The oxygens are -2. There are 3 of them. So it's -6, right? What's the overall charge? Okay. Does everybody see the charges up there, right? Sometimes when I circle charges, people say, why is there a theta there? So, can't win for losing. All right, so the charge is -1, and then it's x plus -6 equals -1, right? If you want to think of it in terms of algebra. So what's the oxidation state on the chlorine have to be? It's +5. Everybody see that? The chlorine is +5. Yeah, so that was my next question. Thank you. Do you want to say it louder?
Lost 5 electrons.
Yeah. So it's gone from 0 to +5. Okay. So each chlorine loses 5 electrons. That's probably the easiest way to show it. Does that make sense? Okay. We good? Okay. Is this good? You guys feeling reasonably comfortable with this? Somewhat comfortable? Should we try one more? One more what? You want me to balance this one? Or? Oh, okay. I was just kind of focusing on it, but okay. Sure, we can do one more. Can I erase this? Is that good? Okay. Okay, so here's a balanced reaction, and I will tell you chlorine likes to be -1. If you look at the periodic table, you can see that it's a halogen. It forms a -1 ion. Okay? And the things that are changing are the zinc and the hydrogen. I'll tell you that too. Okay? So, figure out for each atom the oxidation state, figure out what's changing and by how much, and figure out how many electrons are involved. Should I write that, what I just said on the board? Okay. So find the oxidation state for each atom. Okay, so we're going to find the oxidation state for each atom, find what's changing oxidation states. Once you do that, what's being oxidized, what's being reduced, and then how many electrons are in the reaction. Does that sound good? And I've been neglecting this side of the classroom, sorry. You guys okay?
Actually, I think I'm pretty good.
Okay. Mm-hmm. Mm-hmm.
This has 2 plus 2
Yeah.
because of that.
Yeah.
2. The zinc loses 2 hydrogen atoms.
Yep. I'd say that sounds good. Doing okay?
Starting out.
Okay. Doing okay? Now, I'm guessing if you've ever generated hydrogen in the lab, this is a way to generate it. Since our theme today is hydrogen. Are we ready? People ready? Okay, so pure element zinc, pure element hydrogen, 0. Okay, and again, pedagogically, I try and focus on the simple stuff to kind of, go through and build whatever. If we look at the HCl, hydrogen in compounds is usually +1, right? So the hydrogen's going to be +1. The chlorine is going to be -1. Does that make sense? Okay. And over here, each chlorine is -1. And the zinc is +2, everybody's saying. I would agree. Okay? So we've done the first part. What's changing oxidation states here? There's only 2 things. Remember, you've got an oxidation and reduction, so only 2 things are going to change. One element's going to gain electrons and be reduced. One element's going to lose electrons and be oxidized. Okay? So what is what are the two things that are changing? Is the chlorine changing? No. It's -1 and -1. So it's got to be, there's only two elements left, zinc and hydrogen, right? Okay? So we look at the zinc and we say, oh, that zinc is going from 0 to +2, right? One way to think about this is 2 electrons are products to balance the charge, if you want to think of it that way. I don't know if that helps. If the electrons are a product, it's losing electrons, it's being lost, and we call that oxidized, right? Okay. You can always check for the hydrogen. They're going from +1 to 0, and so we have to have an electron being added. So it's gaining, and that's being reduced. Does this make sense? Everybody's good? Okay. How many electrons are being exchanged here? There's 2. The zinc is losing 2. Each hydrogen is gaining 1, and there are 2, but it's the same electrons. You're counting them separate. It's okay. It's a real common, it's an easy mistake to make. That's why I make the joke about we could pass money back and forth, right? It's the same dollar bill that's going back and forth. They're the same electrons that are being exchanged. So if you're trying to count electrons, it's easier, because you don't have to worry about stoichiometry, if there's something that there's 1 of, because this zinc is losing 2 electrons, so it's a 2 electron change. And then each hydrogen is gaining 1. There are 2 hydrogens, so the hydrogens all together are gaining 2. Does that make sense? So,
I gotta say, I'm still not crystal clear on one thing. When you go to the product side,
uh-huh.
how do you know that chlorine is -1 each? How do you know? Why isn't it -4?
Sure, it's a good question. Do you have I'm going to pull up a periodic table. So the easiest thing to look at here is the chlorine is in group 17. If it can gain 1 electron, it's going to make a noble gas shell. So chloride, think about the sodium chloride, salt, is a -1. So, and one of these is, it gets to be almost like if you're learning a foreign language and you do drill and you sort of like, when you see chlorine, it's not always -1, but if you don't know, -1 is a real safe guess.
Okay.
Does that make sense?
Just go by group then.
Go by group then, yeah. And that's rule 6 that was up there, that if you don't know, it's usually safe to guess by looking at the periodic table, if it's things on the edges. Okay? Is this good? Okay. I wanted to do, I was going to make gloop with you, because it's glue is our theme. It's glue, Elmer's glue plus borax. It's very messy. Do you guys want to do that, or you want to keep working on this? If you've already done it and you know what we're doing, we don't have to do it. I didn't think that we had done it. We made oobleck, which is cornstarch in water, which is also a mess. But when I looked at my notes for the last 2 years, I thought I had done it, but it wasn't in my notes where I wrote stuff up on how to do it. So if you want, you don't have to do it if we've done it before. But so how many people want to make gloop? It's like silly putty? Okay. All right. So, is that okay? We good? All right. So what you're going to need, you're going to need a cup. I got a bunch of cups up here. Come and grab a cup. Okay. You're going to need a spoon, so you need to grab a spoon. Yes. So, so grab a cup and grab a spoon, okay?
How much is,
Okay, I'll put the recipe on the board here in a sec. Thank you. For now, yeah. Okay, I'm going to put one on each corner here.
Can we take one of those, or?
I was just going to put it somewhere where we could maybe spread out a little. I don't know, maybe over here. Okay, so what you need is you mix in your cup 4 spoonfuls of the glue water, and as a recipe, it's equal parts of glue and water. So this is a half a gallon of glue and a half a gallon of water. Okay? All right? I've already mixed it. And then you need about 2 spoonfuls of borax water. If you want, when you put the glue in your cup, you can add some food coloring to it, and then you will get colored silly putty. Okay? Now, you play with it with your hands. That sometimes means that your hands will be green or red or purple or whatever. Okay? So what you're going to do is 1, 2, 3, 4, and then I've got the borax water here. Okay, and I will pour this out into cups. You put twice as much glue water as you do borax water. And it's easier to add the borax water to it. So I will show you that. And you use your own spoon to mix them. Okay, so what happens is, the chemistry is, the borax is what we call a cross-linker. And it will cause the glue molecules to stick together. And what you get, oh, that's pretty good, is like silly putty or slime or snot or whatever. Okay? Does this make sense? It takes the borax a while to dissolve. So I put a metric boatload of borax in there last night. And I just shook it up an awful lot. And I have a baggie of borax somewhere, which means if the police stop me, I'll probably spend a lot of time in jail, because I have this mysterious bag full of white crystals. But, you know, they're probably going to put me in jail for having a empty tank of hydrogen and who knows what else. But anyway, this turned out really well. Have at it. You guys can do it. If you want, you can add some food coloring. Or you can, what? You buy borax. You buy borax. Borax is a laundry additive. So like 20 Mule Team borax you can get at the store. Maybe your grandma put it in the laundry or something. You don't want Boraxo soap. That's something different. Okay? But you can buy a really big box of borax and it'll last you a pretty long time. And then you just basically make a saturated solution of borax water. Okay? Now, I have Ziploc bags, so you can keep your glue slime if you want. It is a lot like silly putty, and I gotta get a spoon for that, sorry. So keep it out of hair, carpets, dog fur. Polymers, what we're making here is a polymer. Plastics are polymers. Yeah, it bounces. Silly putty is a polymer, rubber is a polymer, proteins are polymers. Polymer just comes from the Greek words meaning many parts, right? Or many units, they're linked together. And so proteins are made up of many amino acids. Your DNA is made up of the 4 nucleic acids that are linked together as a polymer with a sugar backbone and all that. Sugars are the basis of starch, which is a polymer, and cellulose, which is what's in wood, which is another polymer. The little plastic cups that we use for the glue experiment were a polypropylene, which is just a long carbon chain with lots of hydrogens off of it. So there's lots of things that are polymers, and all you're doing here is making a polymer. And unlike dried glue, which is kind of hard, this stays fairly wet. It traps water in it, but it also is, it's a different polymer because you're linking it in different ways with the borax. So do you have a question now, or?
I was thinking how I could apply it to my biology.
So yeah, there's lots of polymers in biology. Lots and lots of things in biology are polymers.
I was also thinking like antigen antibody type reaction, where you have.
Oh, okay. I hadn't even thought of that, but sure. Yeah, it's pretty specific. I mean, you can do this with clear glue, which is more expensive. So I bought the Elmer's glue because I have to do this 140 times. Okay. We have a few minutes. I need to cover electrochemistry. Okay. And it's just a few minutes. We've got about a little less than half an hour, okay? When we talk about oxidation reduction, we've seen that electrons are exchanged. And so when you have electrochemistry, all that you do is you separate the oxidation and reduction reactions, and you hook them up with a wire, and you force the electrons to flow through the wire. Okay? And when electrons flow through a wire, we call that electricity. And you can use that flow of electrons to do work. So if you like models, all models are wrong, some models are useful. I get pretty far thinking about electrons flowing through a wire like water flowing through a pipe. If I have water flowing through a pipe, I could put in a turbine or a water wheel and spin it and do work. Water would flow from a higher tank to a lower tank, just like it flows from a higher energy thing to a lower energy thing. You know, we're not going to worry about current, but you could think about the size of the pipe as current and that kind of stuff. Does this make sense? Okay. So, a very old way of generating a current, called the Daniell cell, for the person who first came up with it, is to take zinc and copper. You put the copper into copper 2+, you put the zinc into zinc 2+ in solution, you put a wire, and then you put something called a salt bridge. Essentially, this is a wire for ions. It's gel, like agar gel for biology, okay? And it's got potassium chloride or potassium nitrate dissolved in it. And so for a circuit, all you need is for charges to move. Electrons are flowing this way, and then negative ions continue to flow this way. And that completes the circuit. Does that make sense? Okay. And by separating, when we did the silver tree, or when I did the silver tree, they were right there, and the electrons were exchanged, and the silver grew right at the surface of the copper wire, right? Here what you do is you separate them. You know, it's the offspring. Got to keep them separated. All right? Hey, you're doing fine. 1.1 volts generating all the time. Anyway. Yeah, now we're going to have to pay copyright to offspring because I'm on tape doing this. But anyway. So what happens is you've got this metal and the ion, and metal and the ion. And so in one case, the ion is going to get deposited out on the metal. It's going to go from the metal 2+ ion and get plated out and gain electrons and get reduced and go to metal 0. And then in the other case, things are going to dissolve and get oxidized and go from the metal 0 electrode to the metal 2+. Does this make sense? So all we're doing is we're taking an oxidation reduction reaction, we're splitting the reactants, we're separating them, and forcing the electrons to go through a wire. Okay? Does this make sense? Okay? Now, if you do this properly, and you don't drop it, potato clock is the same thing. Except there, the source of energy are reactions that are going on in the potatoes. Okay? And supposedly you can set, has anybody ever set up a potato clock? Supposedly you can set them up and they run for like months. I kind of worry about the potatoes going bad, but apparently it's okay. All right? And you can do, if you Google it, you can do potato clocks with like pennies and tinfoil and alligator clips. And I've seen pictures of these. I haven't tried them. And if I'd have done that, it'd be a lot easier to fix, but okay. And you can just buy a cheapy watch and hack into it, okay? But the whole idea of electrochemistry is that it's taking redox reactions, oxidation reduction reactions, and forcing the electrons to go through a wire. That's all you got to know about. It's really just a special case of oxidation reduction reactions. Does that make sense? Okay? Now, perhaps I shouldn't have said that's all you got to know, because there's more slides. Here's the water analogy again. If you had different tanks of water at different heights and a complicated system of valves, you could open valves like A and B. B is higher, so the water is going to flow down and up into A. Does that make sense? Okay? Or if I open A and C at the same time, C is higher, the water will flow down and into A. Does that make sense? Okay, I could do 2 more examples, but instead of figuring out exactly how high these things are, what you need to do is predict the direction of flow. Well, you just rank them from highest to lowest. Does that make sense? Okay? So anything that's higher, E is the highest, D I believe is the lowest. You know, E will flow into anything else. D will accept water from anything else, right? And anything else you could just compare. You know, if I open F and C, oh, F is going to flow to C because it's higher. Does this make sense? Okay? All models are useful. Or, I'm sorry, all models are wrong, some models are useful. This is the electrochem version of that. All we do is we show reactions. These are like tanks of water. We show their voltages, which we call a standard potential, and we list them from highest to lowest. Does this make sense? So here, I just say, okay, E is the highest, D is the lowest. Here, I say, oh, fluorine getting reduced to fluoride is the highest. Lithium getting reduced from the ion to the metal is the lowest. Does that make sense? Okay? So what people have found is it's easier to make a list like this than to tabulate every single possibility. Because then all you have to do is you have to compare. So like here, there's 6 tanks. You could figure out, it's like 6 factorial or something, right? There's like 36 or something, possible combinations. There are literally thousands of reduction potentials that people have measured. So if you had every single possible combination, it would be way too complicated to post. So what people do is they just list them, and then we have to have a way to combine them and figure out what the voltage would be. Does this make sense? Are people with me? Okay. So, bless you. We've already seen to have a redox reaction, you need both an oxidation and a reduction. To make an electrochemical cell, which is just a special redox reaction, I still need an oxidation and a reduction. And so what we do is we say, okay, E naught for the cell, which is the voltage, is the reduction minus the oxidation. So what does that mean? Well, let me show you here. The standard, the default, is that we write these all as reductions. Okay? It's easier to pick one way and write them all as reductions. Before 1962, I believe they were all oxidations. So if you find a really old book, they're all backwards. Okay? But the easiest thing to do is say, okay, we're going to write these all as reductions, and we're going to do the voltages for all of these reduction reactions, and we'll list them from the highest voltage down to the lowest. And then the one that's going to be a reduction is the one that's higher, the one that's more positive. Does that make sense? And then you say, well, we need both an oxidation and a reduction, so we can't have 2 reductions. You can't have 2 people giving up their money and it goes nowhere. So you just subtract the one from the other and you flip the sign. The oxidation is the one that you subtract. Does this make a little sense? This is the theory. I'll show you practice in a second. Okay? So here's the Daniell cell again. We've already seen this is the reaction that we had before. Okay? If we write both of these as reductions, and I just took these from the table, the copper is 0.34, which is positive. The zinc is minus 0.76, which is negative. Copper is more positive. It's higher in the list. It will be the reduction. You can look here and you can see copper is being reduced. It's going from 2 plus to 0. Everybody see that? Okay. The zinc is not, I'm sorry, I just burped and whacked the microphone. Sorry. Sorry, all future viewers. But the zinc is not being reduced. It's being oxidized. It's going from 0 to 2 plus. Sorry, 2 plus. Okay? So even though this is written as a reduction, we really need to flip it and make it an oxidation. All we do is we subtract it, and that has the same effect. Okay? So if I take 0.34 and I subtract negative 0.76 from it, that's like adding 0.76 and 0.34, I get 1.1 volts. Now, it's always cool when I do this because I learn things. Historically, the reason why the volt was picked to be the size it is because the Daniell cell, back when they had fairly crude ways of measuring, produces about 1 volt. Now that our ways of measuring are slightly more accurate, it's actually 1.1, but the volt was originally defined so that if you had a Daniell cell, which was fairly easy to make, you could say, oh, here's a volt. It's putting it out. But does this make sense? Is this somewhat clear? Kind of clear? Okay. Let me go through the vocab here and talk about a couple things, and we'll do a couple examples. Okay? Is this good? So, first off, we have to stress here that we're talking about what are called galvanic cells. Galvanic cells comes from the guy, again, relating to biology. He was Italian, Galvani, and he took freshly killed frogs. It's really hard to find good freshly killed frogs nowadays. And he would zap them with electricity, and their legs would twitch. All right? Okay, proving thereby that dead frogs do interesting things and that your nerves are electrical in nature. Okay? And so galvanic cells have a positive voltage, and they're spontaneous. Spontaneous just means that we don't have to do anything and it works on its own. If your car is at the top of the hill and you give it a push and it's in neutral, it will roll down the hill. That's spontaneous. If your car is at the bottom of the hill, it's not going to roll back up. That's non-spontaneous, right? To get it to go back up, if you're at the bottom of the hill, you're out of gas, and the gas station's at the top of the hill, you have to put a lot of work and push the car up. But if you're lucky and the car runs out of gas at the top of the hill, you just have to roll down. That's spontaneous. Does that make sense? Okay? If anybody has a battery, and I'm guessing most of you have, I've got the old-fashioned. I like this because it's, you know, Kirk to Spock, 4 to beam up, right? Flip phones are just like really cool. But anyway, it's got a battery in it. Your iPad has a battery in it. Anything with a battery, the battery is a galvanic cell. It produces energy without you having to do anything except turn on the switch, right? Until it runs out, right? Okay? Does this make sense? So a galvanic cell, it's got a positive potential, a positive voltage. It's a spontaneous reaction. We do electrical work with it. It's a source of energy. A battery is one example, okay? Within the cell, we talked about those two electrodes. They have special names. The anode is where oxidation takes place. The cathode is where reduction takes place. I remember it that the vowels go together and the consonants go together. When I talk to my college students, I say the orientation assistant drank an RC, and they go, what's RC? It's kind of cola, right? Okay. Okay, so oxidation takes place at the anode, reduction takes place at the cathode, all right? Let me show you two more slides and then we'll work a couple examples. There's another kind of cell that you can have. The other kind of cell is called an electrolytic cell. If you know words, electrolytic means electricity and splitting. These are the kinds of cells that you use to pass electricity through stuff and break it up. So when you take water and you split it into hydrogen and oxygen, that's an electrolytic cell. You have to do work and split it, okay? These have a negative potential. They're not spontaneous. You have to do work. So they consume electricity. They need an outside source of energy to run. Again, most nights I forget, but sometimes I remember and charge my battery, okay? When I charge my battery, this actually is then working as an electrolytic cell because it's going backwards. I'm plugging it into the wall. That's an outside source of energy. That energy is flowing in and recharging my battery, okay? Your iPad batteries you have to recharge, okay? Unless you've got the potato clock version, so battery being charged is electrolytic. Splitting water into hydrogen and oxygen is electrolytic. The last thing I want to talk about, this is an example of sort of both electrochemistry and oxidation reduction. But when we talk about galvanic cells, you can also galvanize things. If you build things, you might have galvanized nails. If you look at a lot of metal, it's galvanized. And galvanized just means that you take a metal, typically iron or steel, and you apply a layer of zinc to it. And the zinc prevents rusting. And the reason the zinc prevents rusting is it actually sets up an electrochemical reaction. If it's going to rust anywhere and it's a big hunk of metal, the zinc oxidizes. It's easier for the zinc to oxidize than it is for the iron to oxidize. And so the zinc protects the iron. The iron doesn't rust until the zinc is all gone, okay? So, not the world's best picture with the lights on. There's a very rusty roof. And then the zinc has a pattern. It actually crystallizes on the surface. So galvanized things have this sort of interesting pattern to them. So if you've ever seen like a metal watering can that's not painted, or a bucket, or light poles, nails, lots of things are galvanized, plumbing pipes sometimes. It'll have this pattern to it, and that's a sure sign that it's been galvanized. With bridges and ships, they will put a big block of zinc in the bridge or the ship, attach it with a wire to the iron of the bridge or the metal hull of the ship, and then the zinc gets oxidized preferentially, and they have to go to them periodically and replace it, okay? It's the same idea. If you ever watched Micro Dirty Jobs, they actually had one where they went down into a bridge and had to replace the zinc, okay? Does this make some sense? Okay, let's do, sorry?
Put a big block of zinc in my car.
I would like that, yeah. I don't know if you could. I mean, you know, I carry a lot of crap around in my trunk. Maybe I'll just get some zinc and attach it with a wire to my car and see if that works. Okay? I'm gonna, in a ship or a bridge, it's called a sacrificial anode, but it's essentially the same idea.
They have them on underground fuel tanks attached to
Sure, yeah, unless they're the fiberglass kind. Yeah.
buildings.
Okay, I realize this is a little small. How about silver plus and iron 3? Does that sound good? Should we just, I was going to pick 2 reductions, and then we'll do the cell for that. Does that sound good? So I have picked silver plus. Somebody pick another one, I don't care. Somebody up front that can see. Do you want to do copper? You want to do the silver tree that we just did? Okay, copper. Okay, so we look at this and we say, okay, it's real simple. I just subtract one number from the other. And I subtract the smaller number from the other. So E naught for this is going to be 0.8 minus 0.34. I believe, I could be wrong, but I believe that is 0.46. If I'm wrong, I'm sure you'll let me know. And the video will be posted. No, I'm just kidding. Does that make sense? Now, suppose that you made a mistake. Suppose that you're like, oh, I don't know, I'm supposed to subtract one from the other. This is wrong. Wrong, wrong, wrong. Okay? But if you did it wrong, you would get the right numerical absolute value. It's just the sign is wrong. Does that make sense? It would be negative. And we know, well, this is a galvanic cell. It's spontaneous. It's positive. All I've done is I've swapped them. So I just need to, I get the right number. I just need to make the sign the other way around. Does this make sense? Okay. Now, it's really simple. You take the one that's a reduction, the one that's higher up in the table, and or the one that's a larger value, and you subtract the one that's a smaller value from it. That's all you do to calculate cell voltage. Okay? Should we do some more? Everybody's saying, please, let's do more. I know you got have time to change, so you want to do one more? Okay, what do you want to do? Pick one. Should we do the, it looks like bromine, 1.06. Okay, and something down here. Was that zinc? Okay. Okay, so 1.06 minus negative 0.76, I'm pretty sure is 1.82. Does this make sense? Everybody's good? Okay. Now, I'm going to tell you one thing. Sometimes people start to worry about stoichiometry. Here's one electron, here's two. We don't worry about that. You just subtract. Does that make sense? Okay. Thank you all very much. You've been wonderful. Don't forget to tip your servers. Try the veal. I don't know.